All right, we're going to begin our next problem. And so what we have here is we have basically two rolls of paper. And so you have the one roll that's supported here, and the supports for the other roll have broken. All right, so picture somebody kind of has their hand up holding this one up, and then you pull your hand away. All right, so B is going to be released from rest. So at the start, nothing's spinning. It's just the support's broken, something's holding it in place, and we just pull our hand away, and this thing starts to fall. So both of these rolls, not very big, so we have two 8-kilogram rolls, and the radius of each is 0.9 meters. All right, that'd be out to the edge where the paper is. Okay, 0.09 meters. And so here we have the initial tension in the paper we'd like to find, and we want to find alpha and for both rollers A and B. So the first thing to do is to do a free body diagram. We're going to take the usual coordinate system. So we're going to break these two things apart. So I'm going to deal with them as separate masses. So the moment that I cut that paper and I put a tension in place, this mass is irrelevant to this. So I can write this as a sum of forces relative to just one mass. That's all there'll be. All right. So A is supported. So when I take that support away, I put a force in the Y supporting it there, and I put in a support for the X. However, if you look at the system, there are no other forces in the X. So the question would be, how much force does the support have to supply along the X? Well, 0. So AX will be 0. So I have 8 times gravity. There's the weight. AY will be pushing up, and there will be a tension pulling down out here, which we're going to figure out. The other roller, so again, is separate. So I have replaced the paper connection by a tension. All right. And this will have weight, again, 8 times gravity. And that's all there is. So what we need to do for this problem now is start applying Newton's law so we can figure out. And we see we need to get accelerations, so it's obviously a Newton's law problem. So we'll start with writing equations relative to the piece on top. The logical place to some moments would be here at the center, A. So the only moment, if you look, this is 0, so it's irrelevant, but that and that both point to A, so they don't exert a torque. All we have is this tension that does that. That's obviously going clockwise, so that's minus T times 0.09. Now the moment is obviously in the Z, but we don't, both sides are the same. We really don't need to mention that. All right. And that would be equal to IG alpha. Okay, so this is a disk. 1/2 m r squared alpha A. So we have one equation, two unknowns. Some forces in the Y. 8 times gravity, that's known. AY isn't known, T's not known. So now we're up to 3 unknowns, but 2 equations. We're still 1 down. So we come here, and we've done all we can with this one. So now we go to B. It's logical to take moments at B. So T, it's this way, it'd be going counterclockwise, so positive T times 0.09. 1/2 mr squared alpha B. All right. So now we're 3 equations in, 4 unknowns. So we'll step up a little further. If we sum forces in the Y, okay, now when this thing starts to fall, yeah, this will start to accelerate. So we have another unknown. So now we have 4 equations and 5 unknowns. Okay, T minus 8g equals 8 acceleration to B in the Y. We still need another equation. Where are we going to get one? Well, here's another equation, but it has another unknown in there. So let's think what the acceleration will be here at O. Why am I doing this? Because I can take the acceleration at B related to O, and the acceleration at O is related to what the acceleration is up here, and then you could relate the acceleration at A over to there. So all of that stuff can be related. All right, so let's start looking at this. So let's think about this. When this first breaks, this is a tight connection up here. What you have here, as this moves here, this piece down here moves all together. Okay, that's a tight connection. So to the extent that this moves, this is moving with it. In fact, this is pulling that along. Okay, there's no slack here. So here is 0. It will pull that. So whatever the acceleration is here, it's the exact same acceleration there. All right, well, what's the acceleration at A? Well, that's boring. It's a hinge. It's 0. So the acceleration right here on this paper, what is that? Let's just think what's happening. So on the roller, if we went from here to the roller, it would be the acceleration relative to the roller at this outer edge would be 0 plus alpha cross r minus omega squared r. All right, but what's the initial omega? 0. So the roller just has an basic acceleration alpha cross r. Now, relative to the paper, let's just suppose this did have angular velocity. As the paper came off the roller, it would lose that normal acceleration minus omega squared r. So the acceleration in the paper in any case is simply alpha cross r. And that's being brought to this point. All right? So down here, as the paper comes onto the roller, it would be adopting whatever the acceleration of B is plus alpha cross r minus omega squared r. Any rotation would be being brought in. On the other hand, once again, the moment that you let this go, what's omega relative to B? What's 0 too? Omega A is 0, omega B is 0. So the acceleration right here is exactly what it is up there. So what's really happening is the acceleration is here, and this is kind of like a fixed point, and so B, you can now almost envision B moving relative to it. If that's a fixed point, it would kind of want to turn down. All right. So this equation here is simply stating, because the paper's taught, whatever the acceleration is here, which it will be alpha cross r, omega here is 0, and then so you'll have alpha cross r acceleration down here. And there's no omega here yet either. But now we have 1, 2, 3, 4, 5 equations and 6 unknowns. We still need one more equation. All right? And we're going to get that right here. So ABY, we're just going to relate acceleration in the B. All right? We don't need to worry about acceleration in the X at B because there's no forces in the X. So the acceleration in the X at B will be 0. No forces, no acceleration. It's that simple. So acceleration of O in the Y will be whatever acceleration of B in the Y is, plus alpha cross R to get out here. There is no omega. In a general sense, you would have to add in the minus omega squared R, but omega is 0. So we're just leaving it out. Okay? So that will work out to, this radius is 0.09b, 0.09 alpha b, alpha being the angular velocity of this. So I'm assuming it's counterclockwise positive. We'll let the signs work out for us. So ABY plus 0.09 alpha b equals alpha a times 0.09. I now have 6 equations and 6 unknowns. It's just algebra. Solve it. So I'm not going to go through the algebra because that's all this is. Check the equations. And then I'll leave that to you. But in the end of the day, you'd find that T, what was asked for, the initial tension, is 15.7 newtons. And the acceleration at B is minus 7.85 meters per second squared. Let's see. And here's alpha A is minus 43 radians per second squared. So that makes sense because this is going clockwise. And alpha B is 43 radians per second squared going counterclockwise. So it's going to be spinning this way. This one's coming off clockwise. This one's going counterclockwise. And that's what we have. I have 2 more to do. See you in a moment.